Welcome to this talk about proof of the Nisan-Ronen conjecture, which is joint work with Yorgos Christodoulou, Elias Koutsoupias, and my name is Annamaria Kovacs. The Nisan-Ronen conjecture is about truthful mechanisms for the unrelated machine scheduling problem. So let me first remind you of this problem in its classic original form. Here in the input, we have a matrix of arbitrary non-negative running times of m tasks on n machines. And the goal is to allocate the tasks to the machines so that the makespan is minimized. The makespan is the maximum finish time over all the machines. What you should remember from this notation is that the rows of the matrix correspond to the machines and the columns correspond to the tasks. And the red color indicates the allocation, so which machine gets a task. And also, I will often call the machines players. We will see in the next slide why. Because here we are not interested in just arbitrary scheduling algorithms, but in special algorithms called weakly monotone scheduling algorithms or weakly monotone allocation functions. Because exactly these are the ones that can be complemented by payments to the machines so that then the owner of a machine, who is also called a player or an agent, is motivated to report the running times on his machine truthfully to the scheduling algorithm. And then our weakly monotone algorithm, together with the basically unique truthful payment function, is called the truthful scheduling mechanism. Here you can see the definition of weakly monotone allocations, but actually we don't need these technical details here. Instead, let me show you the simplest and most well-known weakly monotone allocation. This is the allocation of the famous VCG mechanism. It allocates the tasks independently of each other and gives each task to the machine with the smallest running time for that task. This is weakly monotone, as I said. So VCG is a truthful mechanism, but it has a very bad approximation ratio for the makespan objective. As you see in this lower bound instance, here it would be better to distribute the tasks equally, so evenly among the machines, but VCG allocates each task to the first machine and so achieves allocation factor of n. N was the number of the machines. Nisan and Ronen 20 years ago had a famous paper where they initiated the area of mechanism design, and here they defined the strategic version of the unrelated scheduling problem, among other problems. And they conjectured that no weakly monotone allocation can be better than VCG, so none of them can have a better approximation ratio than n, where this is mathematical property of weakly monotone allocations. So it has nothing to do with computational resources or so. Here you can see the lower bound results for this problem over the last 20 years. The tightest results are a proof of the conjecture for the special class of anonymous mechanisms. And for general, so arbitrary truthful mechanisms, we had a lower bound of about square root of n about 2 years ago. And the current result is a proof of the conjecture that is a lower bound of n for the general problem. Now, before I come to the proof of the lower bound, let me start by some preliminaries. A basic idea is to consider only input instances that allow just 2 machines for each task, by setting the other costs of the tasks to some very high value. And such inputs can then be modeled as a graph or a multi-graph, where the vertices correspond to the machines and the edges correspond to the tasks. Moreover, typically we will set one of the tasks values to 0, and we'll call such a task then a trivial task. Obviously, then such a task does not contribute to the optimal makespan. And only in the very end of the proof, we will increase some of these 0 values to obtain a few non-trivial tasks. For example, the input that you see here corresponds to a star graph with values 0 and 1 on every edge. Such a star input, we will also, on such a star input, we will use a special notation, as you see here. The costs of the central machine will be denoted by a vector t, and the costs on the satellite machines will be denoted by a vector s. Notice also that we use here n+1 machines, but we will just sketch a proof for a lower bound of n for simplicity in this talk. Now back to weak monotonicity. Weakly monotone allocations have a very nice geometric illustration. Here for a single machine and 2 tasks, depending on the costs of these tasks on this machine, everything else is fixed. Here we can see the allocation regions. That is, here, for example, the costs for both tasks are small. So this is the region where the machine gets both tasks. This is the region where he gets none of them because both costs are high. Here he only gets task 2, and here he only gets task 1. And weak monotonicity implies that these regions can only have one of these forms, so this one or this one or this one. This is just an illustration, but we will use this illustration. And finally, there is one more important concept for a given machine and a given task, a fixed input. The highest cost, so that the machine still receives that task, will be called a critical value or boundary value, and will be denoted by psi. Yeah? Here is psi j because it's for task j. Here you can see these boundary values, or the boundary value between getting or losing the task 1 for this machine by a red broken line. Here you can see how it depends on the input T2 because the rest of the input is here fixed. So this is the boundary. And now let me finally tell you the most important ideas of our proof. Let us fix an arbitrary weakly monotone allocation. Recall that psi is the boundary value, and the plan is to prove the existence of a machine. Here in this input, it is the machine 0, and a set of tasks with pairwise different other machines, so that the sum of the psi values for these tasks is at least n. Let's say this is the part A of our proof, or property A. And moreover, we will require that even if we set all of these tasks to psi at the same time, even then our 0 machine receives all of these tasks. Observe that from the definition of psi, this does not follow. So the psi values are valid if we otherwise set our task values to 0 and 1, as you see in the figure. Okay, if we found such a set of tasks, then this will be a good lower bound instance, because then the 0 machine receives all these tasks with a makespan of at least n, and the optimal makespan is 1, because we can give the tasks to their other machines, to their different other machines. Good, so now let's start with part A. Why is there such a set of tasks with sum of psi values of at least n? For this, let us consider this boundary function of a task, this boundary value of a task as a function of the other cost of the task on its other machine. Here it is denoted by S. And let's assume for a moment that this function is such a simple linear function, C times S. Now observe that for any given task, these boundary functions on its two different machines are inverse functions. Because here, for example, if the t player, that is the 0 player, receives the task because the t value is small, exactly then the S player does not receive it, and vice versa. In particular, here then the boundary function of the other machine of the task will be then t over c, and c plus psi inverse in the point 1 is then therefore c plus 1 over c, which is at least 2. So now you can imagine approximately how we will get the lower bound. First, we will give symmetric roles to the machines in order to find out which one has the highest sum of psi values. And so the rough idea is at the beginning not to start with a star input, so we don't immediately say which will be the central machine, but with a click. That is, we will use a task for every pair of machines, and then consider the sum of all possible psi values for all these tasks and machines. And because the psi and psi inverse is at least 2 every time, we obtain that this sum in total is at least n times n plus 1. So at least one of the n plus 1 machines must have a sum of psi values that is at least n. So that's the rough idea. But we are not yet done with the part A, because there are some serious difficulties or serious problems that we neglected. The first one is that the psi, the boundary function, is typically or not necessarily linear. But even then, if it's not linear, for the psi plus psi inverse, something similar as this lower bound of 2 holds, namely the integral of psi plus psi inverse, let's say over the interval 0, 1, is always at least 1, as you see immediately in this picture. So this is the sum of these two areas is always at least 1. And therefore, by the mean value theorem, there must exist some value in the interval, some value z, so that psi plus psi inverse of z is at least 2 times z. Good. Now we can consider this integral and apply the mean value theorem for the whole sum of psi functions and obtain straightforward, as before, a common mean value z for all this, for this whole sum, and for the common mean value a central machine I, so that the psi of z on this sum of the psi of the z values on this machine is at least n times z. Straightforward by the above argument. Let's assume that this central machine is machine 0. Good. The other difficulty, the other problem that we neglected, or where I was cheating actually, is that from some point on, I didn't really tell you what should be the fixed instance for which we define our psi functions. In particular, here now, if I set the tasks that we obtained, the tasks of our central machine, if I set their other values now to z, as I should do, during this, the psi functions would change, right? So this is a much deeper problem, actually. And this we resolve as follows. We don't consider a click, but a multi-click. That is, for every pair of machines, we take a huge amount of parallel tasks. And with independent, uniform, random Z values, we will set each task randomly to 0Z or Z0. This is a trivial instance with opt 0. And we will fix this instance until the last step of the proof. And this is the instance for that we define our psi function. So for that we consider our psi functions. And now we would also like that we just have a finitely many different psi functions, and therefore we will round each psi boundary function to some nearby step function. And then for a given pair of machines, now we will consider only the tasks, so only a subset of these parallel tasks, those ones with the same step function that occurs most often for this pair of machines. And now comes a crucial property, it's non-trivial, that even for this restricted set of tasks, this restricted set of edges here, the other tasks are trivial and we will ignore them in the rest of the proof. Even for this set of tasks, the distribution of the Z values is uniform. This is because the allocation of a task in a trivial instance, that is the psi function basically, is independent of the values of its parallel tasks. So you can think of it as if for this fixed pair of machines, we already knew the psi functions of the edges and select the random Z values or set the task values for this pair of machines only after that. Good. So where are we now? Now we have for each pair of machines just a single function, Cij function, or respectively its inverse function. And this is basically the setting that we had before for our click. So by precisely the same argument, now we select mean value Z, common mean value, and the central machine I. And because of this property that the distribution of the Z values is uniform, we will find that many of the tasks will have value 0 on the central machine and precisely this mean value Z on the other machine. In particular, we can then select a set of tasks in form of a star with values 0 and Z, and with this high sum of psi functions. This is basically the part A. In the paper, we call such a set of tasks a nice star. But yes, now we come to part B. Why can we set the 0 values of all these tasks to their psi value at the same time, so that the T machine, the 0 machine, still receives all of these tasks? Here you can see first some illustration of what good and bad things can happen. This is an illustration for 2 tasks. These are 3 different cases. In the first 2 cases, you see that we set both tasks, this is a star of 2 tasks, we set both of them to psi, and still our T machine receives both tasks. This is because the region that the machine gets both tasks is a rectangle. We say that it is a box. Actually, we say that this set of two tasks is a box. It is a star, and in addition, it is a box. So this is a good case. The third case is, here we had, so to say, bad luck, because we set both tasks to T, and therefore now the T machine does not get the tasks. Actually, it doesn't get any of them. Here you can see some illustration for 3 tasks. It's a similar illustration. This is the region where the T machine receives all 3 tasks. In the first case, this set of 3 tasks is a box. In the second, it is not a box. So as you see, what we would actually need is to find a set of tasks, which is a nice star, yeah, with this property, and which is in addition a box. And in the paper, we show the following theorem, that if for every satellite machine we have a huge amount of parallel tasks, then such a multi-star always contains a star which is a box. Actually, most of the stars that it contains will be a box then. So in summary, what we need to find in our multi-click, and we will find it if the multi-click has high enough multiplicity, what we need to find there is for every satellite machine J, we need plenty of parallel tasks with precisely the same Cj boundary function, same step function as boundary function, and for all of these tasks, the same mean value, common mean value Z on their other machines. This is what we need. Then by this theorem that we call box theorem in the paper, this will contain a star which is a box. And then on the tasks of this box, we will set our first values to their psi values. And because it is a box, still the 0 machine receives all of these tasks. So this will be our final lower bound instance with make span or finish time at least n times z on the 0 machine and with optimum z. Here I have some more slides about the proof of the box theorem. So why does every multi-star with high enough multiplicity contain a star which is a box? The proof is by induction on the number of satellites, and the proof also uses that for very small instances, for 2 by 2 matrices, we know exactly which are the weakly monotone allocations because these have been characterized. Now in the induction step, we consider a set of tasks which is a star, and so that all of its proper subsets are stars that are boxes. Now either our big new star is also a box, or so to say there are many boxes of k elements in which case we are done, or it is not a box, but then the region where the T machine receives all the k tasks has such a form. You see the proper subsets are all boxes, but the whole set is not a box. And then we argue that the boundary function pk in these blue points cannot be linear, because if it were linear, then there would still be a proper subset which is not a box, at least for one setting of Sk. It is not a box. Here it is T1, T2, and this figure at least is not a box. So this is excluded. And then we know by the characterization that if it is not linear, then on the other hand, the allocation of the task k and of an arbitrary parallel task of k must be independent. Here we see the independent allocation. And this implies, by a very simple geometric argument, actually you see the geometry here, this implies that if we take out from our star the task K and replace it by an arbitrary parallel task, then we obtain a box. So this was not a box. Here it is 1 dimension smaller than in the previous figure. This was not a box, but now this is a box. So actually we obtain a box by with an arbitrary parallel task of task K, which means that our multi-star contains plenty of stars of K tasks that are boxes. Just that we had a bad luck with our task K before. So this was the sketch of the induction proof of the box theorem, and all in all, this was the sketch of our lower bound proof. And I would like to say thank you for having watched this talk.